This is the Chapter 18 whiteboard lecture covering numerical time and PowerPoint slides 4 through 18. A numerical date is different from relative dating because it anchors the age of the rock along a timeline. So we get an age in years rather than just saying it's older or younger than something else. So to do this, we require a process that operates in the rock at a constant rate over a long period of time. Rocks are very old. So a good example, which has to do with rocks, is counting tree rings. We know that every year a tree grows, it grows one ring. So if we count those rings later, we can count the number of years the tree was growing. To date a rock, we use the decay of radioactive isotopes. That's the process that happens within the rock, operates at a constant time and over a very long period of time. So just some general reminders here as we begin to talk about this process. Atoms are the smallest particle of an element. They contain protons, neutrons, and electrons. And you can see in the figure to the right that we have um, a nucleus, which is the center part in there. That's the nucleus, and that's the part we're going to be most interested in for this process. That contains the protons and the neutrons. The electrons are orbiting around that. So it turns out that the number of protons in a nucleus determines the type of element. So a specific element has a set number of protons in the nucleus. However, the number of neutrons is not always the same. Protons and neutrons both have a mass of 1 atomic mass unit, so we use that to add up the weight of an atom. So isotopes are atoms of the same element, but with different atomic weights. So again, the number of protons is the type of atom. So we're using carbon here as an example, as a shorthand of a C, how we identify carbon. So the number of protons is called the atomic number, and that's the same for every atom of carbon. So you can see we've got 3 isotopes of carbon here, but they all contain 6 protons. That's the atomic number. The atomic weight is actually the sum of the protons and the neutrons. Remember, each one of them weighs 1 atomic mass unit. So if we add them up, we get the atomic weight of the atom. So if we have 6 protons in each one of these isotopes, then we can just do a simple subtraction to figure out how many neutrons, if protons and neutrons together, make up this atomic weight. So if we have 6 protons in this isotope, then we must also have 6 neutrons because 6 plus 6 is 12. We must have 7 neutrons to get us to a weight of 13 in this isotope of carbon, and we must have 8 neutrons to get us to a weight of 14 in this isotope. You might have heard of this isotope here because carbon-14 is a radioactive or unstable isotope of carbon. So there are several different ways in which radioactive isotopes can decay, and we're just going to look at this really simple example first. So we have the nucleus of an unstable or radioactive parent. The red spheres are neutrons, and the blue spheres are protons. So what happens during this simple decay process is that one of the neutrons, and they're using this one right here, spontaneously changes into a proton. So now we have an atomic number that's one more, right? That's the atomic number was the number of protons. So this nucleus now has an additional proton. But the mass of the isotope doesn't change because even though we've changed this neutron into a proton, they weigh the same amount. So we have an increase in the atomic number, but no change in the atomic mass. Like I said, there are several different types of isotope decay, so we're just looking at this very simple one. So if we use our example of carbon-14, we had 6 protons and 14 total particles. So again, that's the atomic weight. If one of the neutrons in here spontaneously becomes a proton, then we have 7 protons instead of 6. But 7 protons isn't carbon anymore. Remember, the number of protons determines the element. And it turns out that once an atom has 7 protons, it's nitrogen. So carbon-14 has decayed to nitrogen-14. So some language we use as we talk about isotope decay. We talk about parent isotope. That is the radioactive isotope that is decaying. And we talk about daughter isotopes. And those are the product of decay. So in our previous example, carbon-14 would have been the parent and nitrogen-14 is the daughter. We measure decay in something called half-life. And a half-life is the time it takes for half of the parent isotope to decay. It turns out it doesn't matter how much, whether you start with a roomful or a thimbleful of that isotope. One half-life is the time it takes for half of it to decay. And that will be the same amount of time, regardless of how much you start with. So we can see this on this graph. Um, we start out here with a box that has 100 blue dots, and that's 100 atoms of the parent isotope. After 50% of them have decayed, so we get to this box, which occurs when 50% of them have decayed, right? Now we have 50 atoms of parent and 50 atoms of daughter. And that, if we drop down, occurs when we have passed through one half-life. So 50% of parent has decayed, we have 50% of daughter, and 50% of each parent and daughter equals the passage of one half-life. So it doesn't matter which atoms we're talking about, and it doesn't matter how many we start with. They just started with 100 because it's a nice round number. Now, as decay continues, in another half-life, we're going to lose half of the remaining parent. So we now only have 50 atoms of parent. So in another half-life, we're going to lose half of that 50, which means we'll just have 25 atoms of parent left. And we add the 25 that decayed, half of the 50, to the daughter, and now we have 75 atoms of daughter. So when we get here to 25% of parent left, we read that down. We have gotten through 2 half-lives. And it just continues. You're always losing half of whatever parent you have remaining. So let's take a rock that has crystallized from a magma and date it. So the beginning of the history of that rock, the lifespan of that rock, starts when the magma has crystallized. And at that time, there is a certain amount of parent isotope in that rock. As time progresses, decay is going to happen. The parent isotope is going to decrease and the daughter isotope is going to increase. And those are happening at the same rate. For every parent that goes away, a daughter is created. So the decay rates, or the half-lives, for various isotopes have been measured in labs, so we know that. That's something we know. If we count how much parent is left in our rock, so we go collect that rock that's been sitting around with the parent decaying and the daughter accumulating. So we go collect it, and we bring it back to the lab, and we count how much parent isotope is left in there. We could also count how much daughter was produced, right? Because the rates at which these are happening are identical. Then we use the decay rate to calculate how long the parent was decaying to produce that much daughter. So it's not that dissimilar from counting tree rings, right? We're counting the amount of daughter that has been produced or the amount of parent that's left, and then we're using the decay rate that we know we've measured to calculate how long the parent has been decaying, and that gives us the age of the rock. So let's walk through an example. Let's say we have measured the daughter isotope in a rock sample, and we have found that 50% of the parent has decayed to daughter. So 50%, if we look on our graph, we have 50% of the parent left. And if we read down the graph, that means one half-life has occurred. So that isotope has been decaying for one half-life. And we know that simply because there's 50% of the parent left. So if 50% is one half-life, we will need to know what the actual half-life of that isotope is. So let's say that isotope has a half-life of 1 million years. Well, the basic formula for calculating the age is going to be the number of half-lives that have passed and the specific half-life for the isotope system we're using. So in this case, the specific half-life is 1 million years. And the number of half-lives is 1, which we know by using the percentage of parent. So all we have to do is say 1 half-life, because that's how much has passed, times 1 million years, because that's the half-life of our system, and we get that this rock is 1 million years old. So another example, let's say we measure the amount of parent in the rock and we find there's only 25%. So 25%, we can use our graph again to find that 25% means that we have gone through 2 half-lives. So 2 half-lives have passed. We know the number of half-lives that have passed. If this is the same isotope that we were looking at in our previous example, we know the half-life is 1 million years. So 2 half-lives times 1 million years gives us an age of 2 million years for this rock. So you're going to be doing some of these calculations in lab, and what you'll be given is always a percentage of either parent or daughter. That's going to allow you to figure out how many half-lives have passed. So this allows you to find this. And then you'll be given this. Or you'll be looking it up on a table. This is one of the tables that you'll be using in your lab. And what this does is it gives you the percentage of parent, the percentage of daughter, the number of half-lives that have elapsed, and then the age of the way to calculate the age of the rock. So this number here comes from this number here. So again, let's just go down and look at let's just go down and look at this 50% again. So if we have 50% of parent, that means we also have 50% of daughter, right? And because that was one half-life is when 50% has decayed. So that means we have one half-life here. And that means that our calculation would be that 1, and then this is something you have to be given. That is the half-life of the system that you're using. So if you have a question that says there's 96% of the parent left in the rock that you're dating, you would come up here and you would say, okay, well, 95.8 is the closest to 96, right? So that means that we read over and the number of half-lives that have elapsed is only 1/16 of a half-life. That's less than a half-life, right? Alternatively, if you're told that you have 12% of parent left, we would find that down here. And again, reading across to the number of half-lives, if we have 12%, that's 3 half-lives that have elapsed. So again, we would take that 3 and we would multiply it by the half-life of the system, which you are given, or there is another table for common isotopes that you'll see, that you'll be looking at. So that's how you will actually do those calculations.